Today, we're jumping into a really clever mathematical idea called the kernel trick. Now, stick with me here because this is a concept that gives a pretty simple algorithm some serious superpowers, letting it solve incredibly complex problems with what is essentially a beautiful shortcut. So, let me ask you this. Imagine you're stuck on the puzzle that feels completely impossible. You've tried everything, but nothing is working. What if the answer isn't about trying harder, but about, well, changing the rules of the game itself? That's really the core idea we're going to unpack today. All right, to get our heads around this, let's start with something really simple. We're going to talk about a machine learning algorithm called a support vector machine, or SVM for short. And at its heart, its job is surprisingly basic. It just draws lines. I mean, look at this. The goal is super clear. We've got two groups of data points, right? The reds and the blues. The SVM's entire reason for being is to find the one single best line that separates them. And when your data is nice and clean like this, it's an absolute master at its job. But here's the key. An SVM isn't just looking for any old line that gets the job done. No, it's on a mission to find the optimal one. It wants to draw a line that creates the widest possible no man's land between itself and the closest points from each group. That big buffer, that margin, gives it the best shot at getting things right when it sees new data later on. So that all sounds fantastic when our data is playing nice and is all lined up. But what happens when the real world, gets messy? What if a simple straight line just isn't going to cut it? And this right here, this gets to the absolute heart of the problem. Most data out there is messy. In this example, one group of dots forms a circle in the middle, and the other group forms a ring around it. Go on. Try to draw one single straight line to separate the blues from the reds. You can't. It's totally impossible. This is what we call non-linearly separable data. So, now we've got a real issue. Our powerful line drawing tool, the SVM, is suddenly useless. It was built for a world of straight lines, and we've just thrown it into a world full of curves. How on earth is it supposed to adapt? Well, the first idea, and maybe the most intuitive one, is if you can't solve the problem on a flat, two-dimensional surface, maybe you just need to add another dimension. This is something called feature mapping. The idea is you take your flat 2D puzzle and you kind of project it up into 3D. So you could, for example, lift that outer ring of red dots up into a new third dimension. And all of a sudden, what was impossible to separate in 2D is now easily separated by a simple flat plane in 3D. You can just slice right between the two groups. And when you project that slice back down to your 2D world, you get the perfect circular line you needed all along. But, and this is a massive but, there is a huge catch. While this whole idea sounds pretty great in theory, actually calculating these new higher dimensions for every single data point is a total computational nightmare. It is incredibly slow, it eats up a ton of memory, and it just doesn't work for big real-world problems. And this is where our hero finally shows up. Instead of taking that long, slow, expensive detour into higher dimensions, we're going to use a brilliant mathematical shortcut that gives us all the power of that complex space without any of the computational pain. This is the kernel trick. And honestly, it's a way to outsmart the problem. It lets the SVM algorithm get the exact same answer it would have found way up in that complex, high-dimensional space, but it does it without ever actually going there. It gets the result without doing any of the heavy lifting. It's like a cheat code. This quote from the source material just nails the magic of it. The key word here is implicitly. The SVM acts as if it's working in a more complicated space, but it never, ever has to actually build or compute that space. It's just pure mathematical elegance. So how does this actually work? Well, it turns out that to draw its line, the SVM doesn't need to know the exact coordinates of every point in some crazy high-dimensional space. All it really needs to know is the relationship between pairs of points, how similar they are. The kernel trick cleverly replaces that slow, brute force calculation with a simple, fast function. This kernel function gives the exact same answer for that relationship, but it does it without ever leaving our original simple 2D space. Okay, so now that we've wrapped our heads around the genius of the concept, let's take a look at how this incredible shortcut is actually used out in the real world. See, the kernel trick isn't a one-size-fits-all thing. It's more like a toolkit. You get to choose different kernel functions to create different kinds of separating lines. The linear kernel, that's your basic straight line. A polynomial kernel can create all sorts of curves to handle more complex layouts. And then there's the RBF kernel. It's the master of complexity, able to draw incredibly flexible shapes to separate even the messiest data you can imagine. And because of this amazing flexibility, you see kernel-powered SVMs absolutely everywhere. They're used in image recognition to tell handwritten digits apart. They're in your email figuring out what's spam. They're used in bioinformatics to classify proteins, and even in finance to spot fraud. And that brings us to the most mind-bending part of this whole story. Remember that RBF kernel, the one for really complex problems? Well, it turns out it's calculating the relationships between points as if they existed in an infinite dimensional space. Yeah, infinite. It's a concept that's pretty much impossible for our brains to visualize, but this one elegant function lets an algorithm solve problems there with a single, fast calculation. That's mathematical beauty right there. So the big takeaway here is really a testament to human ingenuity. The kernel trick takes a dead simple tool, a line drawer, and with one little mathematical substitution, turns it into an absolute powerhouse. It can solve ridiculously complex problems by finding a clever shortcut through dimensions, all without getting bogged down in the computational chaos. And it really makes you wonder, doesn't it? Out there in science, in engineering, maybe even in our own daily lives, what other problems that seem impossible right now are just waiting for a similar flash of insight? What other puzzles are just one clever, game-changing shortcut away from a solution?